Okay, I decided to record this video here for those of you that are still struggling with um, balanced force particle model check 2, which is when given one force I can describe its Newton's third law force pair. And if you are struggling with this, you're totally normal. This is a very difficult um, content piece to master, and Newton had trouble with it too. Um, so this idea starts from the way we define force, right? And if you recall, force is defined as an interaction between two objects that results in a push or a pull. So here's our definition of force, and built into the definition is the fact that there are two objects that we need to be able to identify for every interaction that we describe with the word force. So kind of built into our definition, everything that we're labeling as a force has two ways to look at it, or 2 points of view. So object A has its point of view. What does the force look like if you're object A? And then what does the force look like if you're object B? And this idea that there's this pairing comes really from our definition here. So let's say we have a normal force, which we'll label Fn. Using on by notation, that would be Fn on A by B. By definition, we have another point of view of the same interaction. If there's a normal force on A by B, there has to be a normal force on B by A. I'll show you in a second how these 2 points of view of the same force, that being the normal force interaction between objects A and B, that those 2 points of view are always going to be equal and opposite. So to do this, let's consider 2 people that are involved in a tug-of-war, and I've drawn them here. We're just going to call them person A and person B. And right now I've eliminated the rope just to simplify this so that there are fewer interacting objects. The people are just interacting directly with each other. And so let's start by looking at all of the forces that are acting on A. And the central question we're going to try to resolve here is, if the force on A by B is always equal and opposite to the force on B by A, how does anybody ever win this tug-of-war? Don't those forces always cancel out, leaving an acceleration of 0? So these things never go anywhere. So how do we resolve this? Okay, so we're going to do it by looking at the force diagram for object A and object B. For person A, there are 4 forces. There's a normal force on A by the floor. There's a gravitational force on A by the earth. There's a tension force on A by B. And there's a friction force on A by the floor. These up and down forces will always cancel because person A doesn't accelerate up or down during this tug-of-war. And we know to draw the force diagram this way because by choosing our system as person A, the forces of interest are all the forces seen from object A's point of view. So all these forces start with Fg on A, Ff on A, on A, on A. If we draw the corresponding force diagram, or if we draw the force diagram for B, it looks very similar. It's like a mirror image. But here's what we have. We have Fg on B by Earth. We have Fn on B by floor. We have a tension force on B by A. And we have a frictional force on B by floor. Okay, and if we go back to what we had said previously, that what was built in to the definition of force is that the same interaction. So in our previous example, this normal interaction has 2 points of view. One, what does it look like from A's perspective, and then the other, the normal force, what does it look like from B's perspective? All right, and we can see that there are both points of view of one force in this diagram, and that is the tension force. We see here the tension force from A's point of view, and then on B's force diagram, we see that same tension, that same pulling interaction between A and B, but we see it from B's point of view. Okay, and this idea of those two forces canceling is a broken idea, because you can see that by definition, these 2 points of view will always be on separate force diagrams. So the key thing here is to recognize that the only thing that can be involved in canceling or balancing out a force on A is another force on A. All right. The other point of view of any of these interactions will always be on a different system and can therefore never be involved in canceling or in force balance. So when we come back to the start question of how can person A win a tug of war, we have to answer that question just using forces on object A. So how does A win the tug of war? Well, let's think. For A to win a tug of war, everything's going to start from rest. What has to happen is object A will have to accelerate to the left. So in order for A to accelerate to the left, what we need is a net force on A that points to the left. Again, if we assume that the acceleration is only to the left, I know that these two will balance out. The normal force and the gravitational force will cancel. So the way A wins this tug of war is if the force of friction on A by the floor is greater than the force of tension on A by B. It doesn't matter one bit that the force of tension on A by B is equal and opposite to the force of tension on B by A. That will always be true regardless of who wins this tug of war. It is built into our definition of force. Those 2 points of view are always acting on different systems. But the way we explain why one particular system, in this case A, changes its motion in any way is by looking at all the forces only from A's point of view. So these are two forces, these are opposing forces that are involved in force balance. They act on the same system. These are different points of view of the same interaction, the tension interaction that is between objects A and B. And that is from our definition of force. There will always be those 2 points of view, and we consider them in the context of the relevant system. This would be the one that's relevant for A. This would be the one that's relevant for B when we try to explain the motion of object A or object B. All right, commonly, this is described as Newton's third law, or for every action, there's an equal and opposite reaction. The action in this case is force, and the action can be what that force looks like from one point of view. The reaction is another way of looking at that same force, and they do always go together, but always act on different systems. Okay, it's a tough one. It's hard. It's an easy conclusion, but it's a hard one to recognize when to use. But hopefully this will help you if you're having trouble with it.